Hi everyone. So I want to talk about some of the theories that go beyond the standard model. Effectively, the standard model is set. That is our fundamental understanding of what we know to be true about particle physics, but we also know there's probably something beyond it. And there are a couple suspicious coincidences that are present in the standard model, which initially were used as clues to create a theory called supersymmetry. The two suspicious coincidences are, one of them is here, in that these are the quarks. Remember, they sit in kind of this 2 by 3 pattern. There are 6 fundamental quarks, 3 generations, right? The U, the C, the T, they all share the same kind of properties, except this one's heavier than this one's heavier than this one. The D, S, and B, they all share the same properties except their mass. The same thing happens with the leptons. The electrons and the neutrinos also have 2 or 3 partners associated with them. These are, we call these generations. This is the first, second, third generations. Why are there 3 generations of quarks and leptons? You know, there's no reason why you can't have 3 here, 4 here. Why do they happen to have the same number? Suspicious, that. Also, the electron has the same charge value as the combination of quarks that make up the proton. In other words, the U quark is plus 2/3. This is minus 1/3. The electron's minus 1. If I just multiply by 3, kind of to normalize units, the electron charge has got negative 3. We've got plus 2 minus 1. These integer values are very suspicious. It's like there's some more fundamental charge component that's associated with them. There's some sort of link between these that's hinted. And so these two coincidences kind of speak in the same direction, that there's some connection between the quarks, which all interact amongst themselves through the weak force, the leptons, which all interact amongst themselves through the weak force. There's some sort of connection between the two. And this generates the theory called supersymmetry. The idea is that there's a whole shadow world where basically the properties of these particles are flipped in half, and there's some sort of supersymmetric force. Now there's a fundamental problem with this idea of supersymmetry. If all these particles exist, and none of them have been discovered, so you have to explain that away somehow. If all these particles exist, and if there's some sort of supersymmetric force that's between them, in a way that's similar to the quantum field theory, which is the framework of the entire standard model, then we should expect these particles to transform into one another. But I've said multiple times that the weak force only creates interactions between the green leptons in this picture and the blue quarks in this picture. We never see something that goes from here to here or here to here. But if there is some sort of supersymmetric theory, we would expect that to happen. So you have to somehow explain that away. Maybe it just takes a really, really long time. What it fundamentally means is that, remember, all these quarks kind of decay toward the U quark. It's the least massive of all. And so these have a tendency to filter down and sit in this U quark. But the electron is much less massive than the U quark itself. And so we should expect this U quark every once in a while to decay into an electron in a neutrino combination. Essentially, what that would be, how that would manifest itself is the decay of the proton. So we should, in the same way, we should, in essence, expect hydrogen to be radioactive as its proton decays into an electron and the electrons just fly away. Essentially, these atoms should be fundamentally unstable. Now, there are lots of atoms around. And so you would expect, even if it takes a really long time for something like this to happen, we've got a large number of atoms to play with. Eventually, one of those events ought to occur. And so there have been experiments set up basically looking at huge, quantities of material, waiting to see if some sort of event like this occurs, where a proton decays down into an electron, basically destroying the atom underneath. This has never been observed to happen. And so the current upper bound for the half-life, quote unquote, for the proton, 10 to the 33rd years. That's a huge number, way longer than the entire lifetime of the whole universe. And so this is a pretty significant problem for supersymmetry, and on top of it, there is no evidence that cannot be explained by the standard model. And so, essentially, the theory just doesn't work.